Welcome back, engineers. Let's jump right into today's explainer. We are mapping out the EPA Method 19 data reduction procedures. Specifically, we're going to look at exactly how your team calculates sulfur dioxide emission rates for different fuel types and how to determine sulfur removal efficiencies in your plant's treatment systems. Think of this as your procedural playbook, totally designed to make this regulatory framework crystal clear.
Here is our roadmap for this explainer. We're moving bottom up today. Method 19 application scope, moisture and F factors, calculating SO2 emission rates, ASTM fuel sampling methods, and finally, pretreatment removal efficiency.
All right, Section 1, Method 19 application scope. Let's establish what we're working with.
When you're out there applying this framework on the plant floor, it is absolutely crucial to remember its exact scope. It specifically covers the data reduction procedures to determine emission rates for particulate matter, sulfur dioxide, and nitrogen oxides. But, beyond just raw emissions, it's also your standard for tracking the sulfur removal efficiencies of fuel pretreatment and control devices. That gives you the overall reduction of potential SO2 emissions. Just keep in mind, this method provides the data reduction procedures, not the sample collection procedures themselves.
Moving right along to Section 2, moisture fractions and F factors.
A foundational input for these emission calculations is BWA, which is the moisture fraction of ambient air. And here's a really handy regulatory shortcut for you. Instead of continuously measuring this, the EPA actually allows BWA to default to a constant value of 0.027. Why? Well, because this specific estimate mathematically guarantees your negative calculation errors won't exceed 1.5%, so it safely bounds your compliance math literally anywhere in the world.
But notice the stark contrast here against BWS. While BWA is your ambient baseline, BWS is the actual moisture fraction of your effluent gas. There is no way you can default this one. It absolutely must be directly measured from your plant's effluent stat gas to accurately calculate those emission rates when your pollutant concentrations are taken on a mixed dry or wet basis.
So once you have your moisture fractions locked down, you need to determine your F factors to calculate pollutant emission rates. An F factor is simply the ratio of combustion gas volumes to heat inputs. When your team goes to use these, you're going to follow a systematic three-step dance. First, identify your specific fuel type. Second, select the appropriate factor, either the dry F factor, which excludes water, the wet F factor, which includes all combustion components, or the carbon F factor, which only includes carbon dioxide. And finally, you just apply that selected ratio right to your measured pollutant concentration data.
The specific F factors you use depend entirely on your fuel bunker. For example, anthracite coal has a dry F factor of 2.71 times 10 to the negative 7th, while bituminous coal sits slightly lower at 2.63 times 10 to the negative 7th. Getting these precise numerical differences right is for sure non-negotiable for accurate SO2 emission calculations across different fuel types.
Okay, Section 3, calculating SO2 emission rates. Let's get into the core equations.
Let's anchor this math to your actual physical stack. If your team is measuring both oxygen and pollutant concentrations on a dry basis, equation 19-1 is your primary mathematical tool. It's brilliant. You take your dry pollutant concentration, multiply it by your dry F factor, and then adjust it against your measured dry oxygen percentage. It's straightforward and highly effective.
But what happens if you've got mixed basis readings? Let's say your SO2 concentration is measured on a wet basis, but your oxygen is measured dry. You obviously can't just plug that into the first equation. You have to shift gears to equation 19-3. Notice how it factors in the effluent gas moisture, that BWS we talked about earlier, to correct the wet pollutant concentration back to a state that accurately reflects the true emission rate.
Let's pause for a quick second before we step away from the math desk and head out into the field to discuss physical fuel sampling. Are these technical deep dives helping your team's engineering workflow?
If they are, please take a quick second to subscribe to this explainer channel. We absolutely love making these structured guides, and subscribing ensures we can keep bringing you these highly focused regulatory breakdowns to make your daily operations just a little bit easier.
All right, moving to Section 4, ASTM fuel sampling methods.
So, to determine your sulfur content and gross calorific value, your operators must follow a strict chronological chain of ASTM standards. You kick things off with ASTM D2234 for systematic sample increment spacing, which is evenly spaced based on either time or the weight of the coal passing the collection area. Then, your sample preparation follows D2013, your sulfur content relies on D3177 or 4239, and finally, you calculate your gross calorific value using D5865. Method 19 strictly requires these specific standards to maintain your data integrity.
Now, if your facility is firing liquid fossil fuels instead, the playbook shifts just a bit. You're required to implement continuous sampling protocols from the lot following either ASTM D270 or D4177. And just for context, the lot size here is defined as the weight of product oil intended as one single shipment, like a ship or a barge load.
Finally, Section 5, Pre-Treatment Removal Efficiency.
Let's see how all this builds into our final calculation. It's pretty amazing how these equations perfectly map the physical plant to the math. Equation 19-23 computes the pretreatment efficiency. Then, that efficiency result feeds directly into equation 19-22, combining with the control device removal efficiency to determine your facility's overall percent SO2 reduction. It's a completely linked, closed-loop system.
Zooming in on that pre-treatment calculation with equation 19-23, you can see exactly where the field data comes into play. The specific sulfur content, %S, and the gross calorific values, GCV, that we gathered via those rigorous ASTM sampling methods plug straight into the denominator and numerator here. You are literally mathematically comparing the raw fuel entering the desulfurization facility against the final product fuel leaving it.
So, the really crucial takeaway here is that from those baseline stack moisture estimates all the way to raw coal increment sampling, EPA Method 19 is a fully connected operational loop. Every single variable matters, and every standard ensures compliance. So, what does this all mean for you? How will integrating these exact mathematical standard procedures reshape your engineering team's daily compliance strategy starting tomorrow?